Welcome. In this talk I'll discuss toroidal pinches and in particular the Taylor relaxation and the reverse field pinch configuration. So first I'll introduce one of the major devices used for this study. So there's Zeta was a toroidal pinch designed to compress the plasma to high temperatures, high densities by passing a pulsed current through the plasma. This was originally one of the big claims, was having produced fusion, which later turned out to be due to instabilities, as I'll discuss. But it did lead to a lot of innovations in fusion research, and one of them was that it was noticed that in some periods the plasma could become very quiet, and so the fluctuations that were normally seen suddenly reduced greatly, and the performance suddenly increased. And then this led to J.B. Taylor investigating this and conjectured a solution that the plasma was relaxing under constraint of conserved helicity, and then using the force-free field by Volta's theorem that showed in the previous video, he was able to predict the profiles that would result, and showed that under some circumstances you could produce a reversed toroidal field, so that across the plasma in some places the field is in one direction, and in other places the toroidal field reverses, typically near to the edge of the plasma. So start by looking at zeta and toroidal pinches. So these are pulsed devices, so they're not like tokamaks, where tokamaks are designed to run steady state. Toroidal pinches are really designed to compress the plasma by passing a pulse current through it. And so we have a toroidal machine like this, and then we pass a very large current briefly through the plasma. And this is done using a transformer. So a transformer coil through the middle, which pulses, produces a large electric field around the plasma, and so we produce a current. That current produces a poloidal field. So here this will produce a poloidal field around here, for example. So you produce B theta, very large fields. Just like a Z pinch, this produces a force inwards, and this would compress the plasma. Now there were several approaches to doing this. Obviously it was very quickly found that this was unstable if there was no external magnetic field. And so there were two approaches. There was a fast pinch, where the aim was to compress it fast enough that before the instability could occur. And another approach was to try and stabilize the pinch, stabilize the instabilities by putting a small external field in. So there was a small external toroidal field, so B phi, so much smaller than in a tokamak, and so the safety factor, as you think about in a tokamak, is usually greater than 1. In these toroidal pinches it was typically much less than 1. So this was a small toroidal field, but the idea here was that the field was compressed and so enhanced. So you started with a small toroidal field. As the plasma is compressed, the field is frozen into the plasma. So as the plasma cross-section reduces, the toroidal field also increases, and so this would help to stabilize the plasma. The same process is now being investigated for some laser plasma ideas. So magnetized target fusion, for example, is you apply a relatively weak external field. As the target is compressed, the field is enhanced, and this helps stabilize instabilities. The problem with it, though, is that you have magnetic pressure. As you're compressing the plasma, you're also compressing the toroidal field, and this is of course where the field is coming from. You have to put energy into creating that field, and so that reduces the compression of the plasma. And so there's a key parameter, is something called pinch parameter. It's called theta, as the ratio of the field which is producing the compression, which is this poloidal field, divided by the field which is essentially resisting the compression and stabilizing the plasma, divided by B phi. And in a large aspect ratio, you can just assume that you have a 2 pi A, for example, where here A is this minor radius A, and this is the major radius from axis to here. So this is big R. So from large aspect ratio, you can just assume 2 pi a times b theta is mu naught times the plasma current. And so this gives you an expression for b theta, and you can put this in, just get that your pinch parameter is just and in order to compress the plasma to get as hot as possible, this should be as large as possible, but there's a trade-off between trying to stabilize the plasma, and so having a larger toroidal field reduces the compression. Now remember, tokamaks work quite differently. The tokamaks aren't relying on compression to heat the plasma. Instead, tokamaks use a strong toroidal field to provide stability, and then use other ways of heating the plasma. So in a pinch, so for example zeta, so this A was about 0.5 meter, and this R was about 1.5 meters. So it's a relatively large machine with zeta. And so people thought that this was producing fusion because you were seen in the spectroscopy. They saw the temperatures were very high, saw bursts of neutrons, and so from the limited diagnostics they had, it appeared that they were producing fusion. Unfortunately, as you'll seen in previous videos, this is all kink unstable, and it turned out the kink instabilities were producing these fast particles, which were producing neutrons and were producing a light which was essentially confusing the analysis of the diagnostics. So this led to work to improve the diagnostics, and also led to this idea of a reverse field pinch, which is almost accidental, but it was noticed that when the transformer was turned off, that's when the pulse was finished, that you'd have these interesting phenomena. This is like the plasma current. So you produce a large current, ramp it up, produce a big current, and then this would essentially decay fairly rapidly. You have various instabilities in this region, and there'd be periods where there's relatively gradual decline, and then it would have some kind of a pulse at the end. So this would be where you have some disruption, the plasma essentially is finished and hits the walls. And then during these periods, the change in the current, so the I dot, so this is like the change in current with time, in time along here. So if you mark this region like this, so these kind of signals would look, so you have like this, you have like a whole load of essentially noisy turbulence going on, and then let's see is that there's a quiet period, and then here of course then you get a lot of noise, and then some kind of disruption, and there's a period about a millisecond or so, roughly where this was called a quiescent period. And what was happening is the plasma is relaxing, it's producing this state with the reduced fluctuations, and then eventually of course it runs out of, the plasma is gradually resistive, so the plasma current is gradually running down, and eventually it loses confinement and it's over. But this period here was investigated by J.B. Taylor and others, and they conjectured that essentially the plasma was relaxing due to turbulence, so you have all these fluctuations here, and this turbulence destroys magnetic energy, so it converts it into heat, but it doesn't. It's on a very small scale, so it doesn't affect the overall structure of the field, and so helicity is conserved. And the conjecture also that the toroidal flux is also conserved, so that you have an external field which is being imposed, it's being compressed, and then that external flux is conserved. Okay, so if you have a magnetic field which is relaxing with conserved helicity, this means that you end up with a force-free field. Now in a large aspect ratio machine, which these generally were, so this has a major radius of 1.5 meters and minor radius of 0.5 meter, and obviously after it's being compressed the minor radius is even smaller. So in this limit we can write down an analytic solution. So there's obviously no radial magnetic fields, and then you have these two functions for the poloidal and the toroidal field, and these are two Bessel functions. You can see that there's a function, there are two unknown variables here, there's a mu and there's alpha, and these are just constants, and they're related to the conservation of helicity and to total flux. So you have two constraints and two unknowns, and so from your initial conditions you can work out exactly what this is. It turns out that this is basically just a function of your initial pinch parameter. So you can be related to, so you can relate this mu basically to a theta, a pinch parameter, and you can show that these solutions, so you can plot what these Bessel functions look like. So this is R, and this is, so if you have functions so this is your toroidal field. There's this kind of shape, so it comes down and then at some point crosses the zero axis. So the toroidal field here reverses if this mu is large enough, and then we have the poloidal field. So I'll draw a different colour. So poloidal field is something like this. It's b theta. Again, it kind of goes up, so you have current running through the plasma, so as you go from the axis, the poloidal field goes up and rolls over and reverses as you go outside the current layer, so you have most of the current inside here. And then experimentally, what was found with a wide variety of machines, that this essentially only depends on the pinch parameter, and so what would happen, you see experimentally, is this would be followed very well. Maybe some slight deviation over here. And then your toroidal field would indeed reverse, and then I'll just want this. So this would be experiment. But you have these regimes where if mu is large enough, then this reversal is inside the plasma. So this is kind of essentially mu r, and this point here occurs when mu r is 2.4. So this is just a function of the Bessel function, and so you can work out precisely when this zero crossing occurs. And so if this reverse direction inside the plasma, then you have a reversed field. So if A is the minor radius of the plasma, then if you make mu A bigger than 2.4, then the field will reverse. So the toroidal field particularly. So you have some location in the plasma. So try and draw what this might look like. So you have some different surfaces in the plasma. If I try and draw three surfaces here. So there are some surfaces where the field is wrapping around this. So it's twisting around the plasma. There's one particular surface when it reverses where the field is purely poloidal, and then outside that surface it reverses direction. So I end up with a field which is going backwards. So if that makes sense, so the blue is twisting sort of left to right, the red is where the toroidal field goes to zero, and the green here is where the field is reversed. So this is somewhere over here, for example. And then this is this location here, and then this location will be somewhere inside here. So this threshold of 2.4 was seen on a wide variety of machines, and you can show fairly straightforwardly this corresponds to a theta bigger than or equal to 1.2. And so if your pinch parameter, which you can choose just by changing the current in the plasma or the externally applied field, if you make this large enough, so you make the external toroidal field small enough, then you end up with this state here, where the plasma relaxes into a reversed field configuration. And this started a whole area of research, and they have some potential advantages in that they need a relatively weak external field. So this is still researched as an interesting sort of study for understanding plasma instabilities, and as a potential for improvement towards fusion. These are called reverse field pinches. So more recently there was some work in 2009 or so looking at what happens when you go at even higher pinch parameters. It was found that the plasma can relax into a state with broken symmetry, and so you end up with a helical plasma which has even higher performance. It's still not as good as a tokamak, for example, but has relatively high performance. And this is the reference. So it's Lorenzini et al. Nature Physics, Volume 5, page 270. And this was called the Shax configuration. So if you're interested in reading more about reverse field pinches, there's a nice review from 1980 by Bowden and Newton. So it's published in Nuclear Fusion, Volume 20, 1980, and page 1255. Okay, thank you.